I'll be talking about flooding. There is a connection to the last presentation I'll mention as I get to it, but mostly I'm talking about how changing sea levels are affecting us here in the San Francisco Bay Area and how we're thinking about that in relation to European and Asian models of adapting to flooding and what we think the future of that might be translatable or scalable to other coastal conditions in the global south and elsewhere. So I just want to remind everyone, we didn't have cities during the last fast periods of sea level rise. This chart shows the last 24,000 years. I originally came to urban design from geology. So as a person who studied glaciers, I never thought I would connect the two. And here I am, of course, now having to watch the glacial literature all the time. But we invented cities during a period of very slow sea level rise. So we're going to have to reinvent. Today, actual sea level rise is tracking a path to about 0.12 meters of sea level rise by 2030. So that's on the middle path out of the possible concentration pathways. But it's important to recognize that it's not just a projection, it is happening. Here in California, the state government has given us guidance in public agencies to consider 1 meter of sea level rise for low-cost, non-permanent investments, to consider 2 meters of sea level rise for high-cost permanent investments, and for truly expensive things like new highways and new sewage treatment facilities or major investments in old ones, we should be considering 3 meters of sea level rise. So that's been helpful, although it's considered very challenging by public agencies here. Just wanted to give you that context. And then at least one take on what the context is in the United Kingdom and Ireland and the Northwestern European coast. I would think these are the areas in red that would benefit the most from the kinds of ideas I'll be talking about. The Dutch have known for a long time that sea level is rising, and that not only is sea level rising, but local rain intensity is increasing, river flooding is increasing because of rain intensity upstream. And most importantly for our conversation, groundwater is also rising. And because they have an extensive national network of pumps, they deal with that by pumping, mechanical pumping. The rest of the world doesn't have mechanical pumping in an extensive system in cities. And so what we're looking at in the future is that as sea level rises, groundwater near the coast will also rise. And that could, and we expect that it will, inundate more hectares of land than the lateral movement of sea level alone, of seawater. And even if we build structures at the shoreline to block those, the waves of the sea, for example, the groundwater could still rise and inundate those urban areas. When it rises, groundwater infiltrates storm and sanitary pipes and takes away their capacity, takes away their functional value. People can no longer flush toilets or drain districts of stormwater. We see this already happening here in the Bay Area. We see maintenance holes where water comes up at high tide. We've seen this in New York, in Miami. The systems we designed to take rainwater away are the primary pathway for tidal water to come up into the cities and cause spot flooding at this point. As groundwater comes up, it's going to change the dynamics of how contamination moves in the soil. And around the Bay Area in San Francisco, we have about 50 contaminated sites that have been capped in place, but not lined from below. So this particular one is owned by AstraZeneca, and 4,000 units of housing are planned to be built on this highly contaminated site, although the sea is right there to the left, and seawater and groundwater will be rising into the contaminated soil. So that's a very immediate human health risk that we're very concerned about. It could be happening now. What happens in this quick illustration of how this works is the seawater on the left, the darker blue, rises. And as that happens, the groundwater near the coast rises pretty much at the same amount within a kilometer or so of the coast. And it won't be 1-to-1 farther in, but it does still rise farther inland as well. And it discharges. It discharges to surface streams, it discharges to cracked pipes, and eventually it floods. And that flooding will, as I said, be a kind of toxic soup if our toxic soils are inundated by rising groundwater. And it will occur even though we may have levees on the coast, because the water is coming up from below the levees. It's like the toe of the ocean is pushing up the pillow of fresh groundwater. And what a disappointment it's going to be to people who expend billions of dollars to build levees and then discover that the area behind them could flood anyway. This is what the city of San Francisco looks like on its shoreline at a high tide now. In an extra high tide with a low pressure weather system, it floods, and the ocean, that's the ocean, comes right onto the street. And that's what we're coping with. That's what we're seeing. But what's happening underground is even more damaging, because both saltwater groundwater and freshwater groundwater could be corroding building foundations. And as we saw with the condominium collapse in Florida over the last summer, that's going to have structural implications, and conventional buildings are going to fail. So even though there's a kind of typology for adaptation designs that are at the coast itself, everything from movable gates in Rotterdam or London to New Orleans, fixed flood walls, to dikes and canals, and the new era of nature-based strategies like the sand engine or like wetlands that we're using here in the Bay Area. The trick is, what will the urban districts be like on the inside? What is the relationship going to be like? Pairing a wine with dinner, pairing a coastal strategy, a structural strategy with an urban district, because the nature-based strategies are going to not be as predictable. We're going to need urban districts on the inside of strategies like the sand engine or a wetland edge, tidal marshes, to be more robust. And what that means in international terms now is more people are looking at floodable districts, and districts that means districts that can get wet without suffering a lot of damage, and certainly without danger of loss of life. So from Japan, we have a particularly interesting example called the Superdyke. This is a photo of the Superdyke. It's kind of hard to see, actually, because it's not super tall, but it does have buildings on top. And it's a change from about a 30-foot high, 100 meters wide, 10 meters tall and 100 meters wide original dike, to what they've done now, where they've not made it taller, but made it very much wider. Now it's something like 300 meters wide, and it's terraced on the back, so that if the river does ever overtop this structure, the water would land on a terrace that's canted back towards the river and provide time as floodwater pools on this terrace before it spills over and pools on the next level. So it's giving people more time to evacuate, and it's so big, it's like a topographic ridge. It can't fail when it's overtopped. And that's something that we're going to have to learn from in the rest of the world. It's also an example that's stood the test of seismic events, but it requires a lot of sand and gravel to build. I'll say more about that in a little bit, how having different materials available to you in particular regions gives you different options. And they have a lot of sand and gravel available in Japan from steep rivers. In Germany, the Hafen City is a classic case of floodable development now. And it's a warehouse district. Of course, it was a warehouse district at their port with the natural levee behind it. And this is a development that was built with a hardened first story, so flooding can occur without causing any damage to residential areas. It's what we'd call a tiered or terraced version of floodable development, where, like the Superdyke, it's built up. And what's inside that hardened first story is parking garages or just compacted earth. Here's a view from the Promenade here. I'm sure many of you have been here, but it's worth seeing it as a flood event might occur. And if you watch the lower image, I'll show where the water goes. At high tide, it's right on the face of that conventional seawall. But in a storm flood, it's on the hardened face of the buildings. In the upper image, that would be right here. So it's set up to flood, to allow that flooding to occur on the lower terraces. And then on the interior of what's essentially a sort of finger pattern of wharves, the interior is higher than the exterior, and there's a second story system of circulation to allow people to stay and get around, and even a small ambulance can get around in a flood setting, in a flood condition. So it's floodable and no one has to evacuate. And during an actual flood, people put their cars into waterproof parking garages and then can take their families down to the edge of the flooding and see it, which allows people to use their natural intelligence to understand what's happening in the world around them in a way that living behind flood walls, where you can't see the world around you and how the water is rising and falling, doesn't let you learn. So what's wonderful about this is that families come down and kids grow up understanding that that flood level is rising, and that eventually they'll have to think about how to raise the terraces even higher. And the future of development in the Hafen City is likely to be mid-rise buildings with their foundations in the water, in the canals. And that's something that can be done in landscapes where there isn't a seismic activity, there are no earthquakes, but it would be much more difficult and more expensive to do where there are earthquakes. So it's a good strategy for most of Europe and other parts of the world where there aren't earthquakes, but not so good for parts of the world where there are earthquakes. Steiger Island is a relatively new development in Amsterdam. It uses a different strategy to be floodable. So instead of building up, this is a situation where the Dutch have built 73 floating townhouses attached to fixed pilings and fixed wharves. I'll show you a couple more images of what that looks like, in a situation where tide gates control the water levels. So it's not on the surface of an ocean section or a bay, it's in a very controlled pond situation. That's what it looks like from the side. This was built as an affordable housing development. It used all prefabricated units. This interior part is the floating part. And it used relatively inexpensive materials and was subsidized so that it would function as an affordable development. And this is what it looks like on the deck of one of these townhouse units. The lower floor is the pontoon, but it's also occupiable, not as a bedroom. That's against the rules. But in these floating townhouse units, you also have to think about which wall you put the piano on and which wall you put the bookcase on. You have to balance and think about that as part of the way you live. So here in the Pacific Rim, we have a different situation. All of these countries are affected by seismic activity, all of these coastlines. So some of the Dutch and German solutions don't work for us. Here in the San Francisco Bay Area, the pink-purple lines show our earthquake fault lines, and you can see they surround this area at the edge of the bay. So we have to choose strategies that will work with an earthquake. The other aspect of the earthquake is when you have urban fill material that was put on top of old wetland soils, you get extreme shaking during an earthquake event, and the material that's been dumped onto the old wetland soils can behave like a liquid. That's called liquefaction. And you can see that most of the Bay Area is susceptible to liquefaction and extreme shaking. This is what it looked like in New Zealand, in Christchurch, when the soil next to the Avon River, which was had high groundwater conditions, behaved like a liquid during an earthquake event. Just for a minute, the soil behaved like a liquid. This car dropped in, and the house behind it there experienced lateral spreading, which means that the foundations and the structure lost contact with each other. But after the event, as soon as the energy wave of the earthquake is over, the soil hardens, and then this car had to be dug out. Luckily, nobody was in this car. This is another image from Christchurch in New Zealand, and it shows a woman trying to clear a drain who lives near the coastline. And actually, the water has come up through her drain. So the problem isn't that something is blocking surface water from draining out. The problem is that the ocean is coming up the drain. So you can see that she's not going to be successful in clearing that puddle. That's just going to get bigger and bigger with each year of sea level rise. So what would an adaptive urban district look like in a kind of typology that would help us understand where we can do what? I think of it as if you have abundant sand and gravel or limited sand and gravel, you've got very different conditions. And if you've got no seismic risk or very low or high seismic risk, you have different conditions. So I think of the Hafen City or the Hamburg Harbor City example as being a condition that you could build if you have limited sediment and you have low seismic activity or non-existent. I think of the Dutch Superdyke, which I'm not showing images of, but it's a very well-known now nature-based strategy where they moved 21 million cubic meters of sand. They have abundant sand to try to protect their coast. That's something you can do, obviously, if you have abundant sand. And then the Superdyke in Osaka was built, again, with abundant sand and gravel, and it works for high seismic activity region. It's very stable because of the way the materials have been stacked geotechnically. But it wouldn't work in a situation like the San Francisco Bay where we don't have much sand and gravel. So what might work for us out of those different types I showed is something more like the Steiger Island floating units strategy. So that's what we've begun to look at. It's been permitted in the city of San Jose, which is the largest city now in the San Francisco region. So Pacific Rim strategies that help us address seismic activity, biodiversity, maintain high water quality, and think about rising groundwater are the ones we're looking for. And in 2016, San Francisco regional residents voted to tax themselves to build 40,000 hectares of tidal marshes to adapt to sea level rise in one of the first regional votes that tested whether or not people are ready to start paying for this kind of adaptation. We've been talking about using that strategy of tidal marshes with a strategy of artificial ponds. So what we're talking about is my former colleague, Rich Haig, described as the essence of landscape architecture. We're going to dig a hole and make a mound. So we're going to dig ponds, excavate artificial ponds where the land is now dry-ish, take that sediment where it's clean and use it to build a wedge of tidal marsh on the bay side. So that's essentially the strategy. And we're designing ideas for floating units that are on shared decking instead of every tub being on its own bottom, like the Steiger Island example, because in that kind of an approach, you don't have to worry about which wall the piano is on and which wall the bookcase is on. Everyone shares the same decking inside one of these artificial ponds, and tide gates allow you to control how much of the tide enters and leaves each pond. An excavated material is used to add to a big habitat wedge on the bay side, because we can't proceed with this adaptation without continuing to build our tidal marshes, because we have very strict federal laws about biodiversity. So we have to do something to preserve that biodiversity as we grow, and it serves us as a way to reduce wave energy, in addition to providing support for biodiversity. So this was the drawing we used in a competition that became, I think, very interesting to people in the Bay Area. And it shows 3-story prefabricated units on shared decking with pontoons, probably not large enough. We're early in our studies of this now. And that's the kind of strategy we're looking at that would allow us to adapt to living with a higher groundwater condition. We're essentially expressing the groundwater condition in these ponds, managing water quality using the landscape around the ponds, and then living in the ponds. And this is an example of one of those, it's a student exploration, but it's a useful one. It's showing shared decking, stacked units, and then a tidal condition around it. And I'll show you how it goes from low tide to mean tide. You can see a landform of levees surrounding the pond, the artificial pond. And then at high tide, you can see that those landscapes are still intact. But as we add sea level rise to it, with 3 feet of sea level rise, it's pretty reasonable. I still feel like those landforms could do their work of supporting that tidal city. But at 6 feet of sea level rise, we think that the landscapes wouldn't perform. The levees would be subject to failure during an earthquake event. And while nobody would lose their life, all that would happen is this decking would drop to the bottom on top of the pontoons, and things might be canted, but nobody would die. We think that we would have to move this system of tidal cities inland, possibly with every meter or so of sea level rise. But what it does is gives investment in housing development certainty for a period of time. And that's what we need. We need to know that we can build housing that would be safe and secure for a period of time. And then that we would kind of roll up the carpet as we leave and move this sort of floodable development. This is a different example in a different location, back inland, and replace the ponds that we've excavated for these floating districts with a new wetland condition. Essentially, dig new holes, fill the old holes, and allow wetlands to migrate into that newly flattened landscape. So it's a fundamentally landscape-driven strategy for how urban districts might be able to adapt. And it's a strategy that we think could scale if people have more labor, but less money for construction. There would be ways to do this because all traditional societies had some version of floating architecture that developed near the coast. So these are actually quite old ideas, and the technology is something that everyone can access at different scales of labor and capital investment. And I'll leave you with that thought. I think we transition to the next speaker rather than taking questions.
Thank you so much, Kristina. That was deeply, deeply fascinating.